So for the next example, I defined a piecewise function, which maybe is a little bit clunky because we don't do a lot of piecewise functions in algebra. But in order to talk about left-hand limits and right-hand limits and make the left-hand limit different than the right-hand limit, piecewise functions are the best functions for that. So this function is equal to 3x, and so this graph right here is, I'll say it's y equal to 3x. You could say f of x equals to 3x for x less than 2. And this graph up here is the graph of y equals to 2x minus 1 for x bigger than 2. So right here is 2 on my x-axis. To the right of 2, I get the graph of 2x minus 1. To the left of 2, I get the graph of 3x. You will notice that the point 26 is marked with an open circle and the point 23 is marked with a closed circle. For each one of the pieces, if I plug 2 in, I get a value. For the top one, if I plug 2 in, I get 6. For the bottom one, if I plug 2 in, I get 3. The reason the point 26 and the point 23 are the points that I marked is because those are the values I get when I plug 2 into each one of these functions. The reason this point is marked with a solid circle and that point is marked with an open circle, this or equal to sign produces a solid circle because that's actually a point on the function, part of the function, and it belongs marked with a solid circle. And this one, because it doesn't have an or equal to, I get an open circle. And so each one of these, this is just the graph of y equals 3x. It would go forever, this graph, but this says I only want the portion of the graph that's to the left of 2. And this is 2, so the left of 2. This, again, this graph too would extend forever and the graphs would eventually cross, but this one only wants the portions of the graph to the right of 2. So this is a picture of this function. Now let me find a left-hand limit and then a right-hand limit as x approaches 2, because 2 is the kind of the interesting number here. So how do I find a left-hand limit as x approaches 2? Well, I start by taking numbers that are less than 2. So this is for the left-hand limit. So I need to take numbers that are smaller than 2. And so I started off with the number 1.5. I said 1.5 is definitely smaller than 2. And I went and decided, where do I need to plug it? Since 1.5 is less than 2, it needs to go in the top function. Any number that I'm going to plug into the function that's less than 2 goes into the top function. So I plugged in 1.5 into the top function and got 3 times 1.5, and I got 4.5. So that's the point. As I'm trying to find my left-hand limit, I'm plugging numbers that are less than 2, but not equal to 2. And each one of those, when I plug them in, it's going to go into the top function, because the top function, I can plug only numbers that are less than 2. Numbers that are equal to 2 or bigger than 2 go into the bottom function. If I continue to find my left-hand limit, so first I plugged in 1.5 and got 4.5. And now I'm going to plug in 1.9 and into the top function, because 1.9 is less than 2. When I plug in 1.9, I get 5.7. So the first point that I found was about there. The second point I found is about there. That's enough for me to believe what the left-hand limit is. I believe that the limit as x approaches 2, but only plugging numbers that are smaller than 2 in, of this function f of x, it's going to be 6. And I think I do one more point just to make you believe it. So when I do the third point, so I started off at 1.5 for the x, got 4.5 for the y, then 1.9 for the x, got 5.7 for the y, and then lastly, I picked 1.99 for the x, and algebraically I got 5.97 for the y. I don't have to plug, infinitely many points in. Once I can see where the y values are going, I can stop. And if I have a graph, I already know where the y values are going. Usually they approach any open or closed circle that is on the graph that's appropriate. So I believe I can make a conclusion now about the left-hand limit. I can say, as I plug in values of x into the function that are closer than 2 but remain smaller than 2, what happens? As the values of x that are smaller than 2, and I plug them into the function as I get closer to 2, the y values get closer to 6. So the left-hand limit, the limit as x approaches 2 with the little minus sign, meaning plugging numbers less than 2, is going to be 6. So again, this is finding the left-hand limit. Finding the left-hand limit, that little minus sign means I'm plugging numbers in that are less than the given number. And graphically, it's to the left of that value on the x-axis. Now let me do the right-hand limit. To do the right-hand limit, I need to plug in numbers that are bigger than 2. So I started off by plugging in 2.5. Immediately, because this is a piecewise function, I have to know what piece to plug it in. The top piece I plug into for numbers that are less than 2. The bottom piece I plug in for numbers that are 2 and bigger. So when I went to evaluate it, I put the 2.5 into the bottom function. And when I did that, I got 4, and I plotted the point. You'll notice now the point's coming north of the 0.23. On the last sequence, my points were coming in from the south and going north. Now my points are going to come in from the north and going south. So as I'm trying to find a right-hand limit, I just randomly take numbers that are bigger than 2, plug them in, and see if there's a pattern in the y's. So first I started with 2.5, I plugged it in and got 4. And then on this screen I plug in 2.1. Similarly, when I plug in 2.1, because 2.1 is bigger than 2, I plug it into the bottom function, and apparently if you do the math on your calculator, you get 3.2. And that point is almost already on the 0.23. I'm already comfortable enough to say I believe that the right-hand limit is 3, but I don't have to commit to that yet. I can continue to go. And I did one more point. I plugged in 2.01, plugged it into the top function because 2.01 is bigger than 2, and when I plugged it in, I got 3.02. This is enough for me to believe that the right-hand limit's going to be 3. As I take numbers that are bigger than 2, but getting progressively closer to 2, the y's are getting progressively closer to 3. So I believe the right-hand limit is 3. And that's what I'm going to say in the next sheet. So now I can make a conclusion about the y values that my points are approaching as the x values get closer to 2 but remain larger than 2. Each of these statements are equivalent. As the values of x that are larger than 2 get closer to 2, the y values get closer to 3. And the right-hand limit, the limit as x approaches to 2 with a little plus sign, is equal to 3. Again, this process is called finding the right-hand limit. It's a one-sided limit. So for the two examples I did, the first example, I did the left-hand limit, which was 6. I did the right-hand limit, which was 3. In the first example on the first video, the left-hand limit was 8, the right-hand limit was 8. The left and the right-hand limits equaled each other. Unlike the first example where the left-hand limit and the right-hand limits were the same number, here the left-hand limits and the right-hand limits were different numbers. So the left-hand limit was 6, the right-hand limit was 3. The two-sided limit, when I don't write the minus sign or the plus sign, it doesn't exist. This two-sided limit doesn't exist. Two-sided limits only exist if the left-hand limit and the right-hand limit come out to be the same number. And that's what I say right on this sheet here, that a two-sided limit only exists when the left-hand limit and the right-hand limits are equal. And this is a semi-formal definition of a concept of a two-sided limit. So I'd say the limit as x approaches some value of a of function f of x is L, provided the two-sided limit of the function, this is just saying this is the two-sided limit of the function. This is saying that if the left-hand limit is equal to L and the right-hand limit equals to L, then the two-sided limit is equal to L. So for a limit to equal L as x approaches a of some function f of x, that means that the left-hand limit needs to be L and the right-hand limit needs to be L. I'm debating on what to do next. The next thing I have in my notes is to do limits at infinity. And yeah, I think it's fine. I think this is not that complicated of a concept. We could sneak it in, and then we'll just keep plowing through the theory and eventually get to the homework. So we can extend the idea of a limit from just a number like a limit at 2 or a limit at 4 to a limit at infinity. And limits at infinity are by definition going to be a one-sided limit, specifically because there's only one side of infinity. There's either numbers that are smaller than positive infinity or bigger than negative infinity. There's not numbers that are bigger than positive infinity. There's not numbers less than negative infinity. So I sketched a graph of the function 2 plus 1 over x and got this lovely picture right here. And I want to find the limit as x approaches infinity. And the limit as x approaches infinity is the y value that the graph approaches as x gets closer to infinity. So what I've done here is I've drawn a picture, probably borrowed this from Google because I don't know how to put the function name on the graph at the same time, but this is supposed to show me this horizontal asymptote that's drawn that you learned in college algebra. What this means is that little dashed line means as if I extend this dashed line in either direction, the graph's just going to hover right above or right below that dashed line. So this function, it's supposed to extend forever to the far right edge of the x-axis. And it would be proper to say the limit as the function approaches infinity. So the y value that the function gets closer to as the x's get closer to infinity. So here I put in positive infinity on the x-axis, and every single point, if I go out to the x-axis and I look up to the graph, the point that I'd be staring at is going to be microscopically above this dashed line, and every point on this dashed line has a y coordinate of 2. So because this graph going off to the right flattens out to the line y equal to 2, we'd say the limit as x approaches positive infinity is 2. I can do this with a table, but for right now I just want to just do it visually. This is a one-sided limit as there's no numbers greater than infinity. Similarly, I can look the other direction. On the far left edge of the x-axis, there's a negative infinity. And as I march off to the far left edge of the graph and I look up to the graph, the points that I see, they're all going to be hovering right on this horizontal line. That horizontal line is the line y equal to 2 again. And so I'd say the limit as x approaches negative infinity is also 2. The left and the right hand limits, the positive infinity and negative infinity limits don't need to be the same. So I graphed the function 5x over the square root of x squared plus 1, and the limit at positive infinity, which is where the graph flattens out to as I go to the far right edge of the x-axis, is different as the limit as x approaches negative infinity, which is the y coordinate where the graph flattens out as I go to the far left edge of the x-axis. I put these dotted lines in just to show you what the limit is. So this says as I go far and far out to the right edge, that this graph isn't going to vary from this dashed line at all. The y coordinate of that dashed line is 5. So as I march off to the far right edge of the x-axis, the limit as x approaches positive infinity is going to be positive 5. That's the y coordinate of this horizontal line that the graph is drawn to as the x's get bigger and more positive. This bottom part of this graph is for the limit as x approaches negative infinity. As I trace along this graph and get further and further to the left of the origin all the way towards negative infinity, the bottom part of this graph is going towards the dashed line that has y equal to negative 5. So I'd say the limit as x approaches negative infinity is negative 5. So limits at infinity, if the graphs flatten out, it's just the y coordinate of where they flatten out, and I always try to draw it with some sort of dashed horizontal line to indicate what the limit is. Graphs don't need to flatten out when we get to the far right edge or the far left edge of the x-axis. And when that happens, the limit doesn't exist. So I graphed this function negative 0.01 times x to the third power. And if I wanted to find the limit as x approaches infinity, so I'd march over to the far right edge of the x-axis and I'd look for the graph. Well, the graph didn't stabilize. It kept going down forever. This graph keeps going down forever. It makes it down to the bottom of the y-axis. I would say the limit as x approaches infinity is the y-coordinates of these points, and these points, because they're beneath the, because they're in the negative y direction, I would say this limit is negative infinity, because as I get closer and closer to the far right edge of the x-axis and look to the graph, it didn't flatten out, so I don't get a number for my infinity, for my limit, and it goes down, and down is a negative direction. So I'd say the limit as x approaches infinity of this function is negative infinity. And the opposite direction, if I marched out to the far left edge of the x-axis to find the limit as x approaches negative infinity, I'd march out to the far left edge of the x-axis. The graph doesn't flatten out, so the limit doesn't exist. And I'd look up, I'd see the graph goes high, and the positive direction that I'm looking up to is the positive y direction, and the top of the y-axis is infinity. So I'd say that the limit as x approaches positive infinity is negative infinity. The limit as x approaches negative infinity is positive infinity. So I'm also able to find limits without doing any sort of graph. And that's what I want to do next. I'm going to find a left-hand limit and a right-hand limit. And I'm going to start exploiting my calculator's ability to do tables. So if I want to find the left-hand limit of the function 3x plus 1 as I plug in numbers that are less than 2, I need to plan out a few numbers that are less than 2, plug them into the function, and see if I can get a prediction on what the y's are getting closer to. Similarly, if I want to take the same function and do the right-hand limit as x approaches 2, then I need to plan out some numbers that are bigger than 2 but progressively closer to 2 and see if there's a y value that we get closer to. So let me laze this up right now. Pull out my calculator. Into my y equals, put the function 3x plus 1. There might be better things to do than I'm doing right now, but I'm just going to graph this, do zoom standard. I don't necessarily need to see the graph, but I think it's going to force it upon me. Really? Y equals 3x plus 1, zoom standard. This thing should show up. There it is. Now let me plug in 1.5. To plug in 1.5, I hit the second button. So the second button first, and then my calc key, and then hit enter on number 1 that says value. And now I'm going to type in 1.5 and hit enter. When I plug in 1.5, I get 5.5. Now I'm going to type the number 1.9 and hit enter. When I plug in 1.9, I get 6.7. So again, I'd go second, trace calc, hit enter on value, and now I'm going to plug in 1.99. When I plug in 1.99, I get 6.97. And lastly, when I plug in 1.999, I get 6.997. I feel good about what this left-hand limit is. Each one of these numbers is less than 7, but they're getting progressively closer to 7. I believe that the limit as x approaches 2 with numbers less than 2 of the function 3x plus 1 is 7. Let me fill out this table for the right-hand limit now. So I'm going to plug in 2.5, and when I plug in 2.5, I get 8.5. And now I'm going to plug in 2.1, and when I plug in 2.1, I get 7.3. And then 2.01, when I plug in oh, I can't do that. Yeah. When I plug in 2.01, I get 7.03. And when I plug in 2.001, I get 7.003. So again, I probably feel pretty comfortable that this right-hand limit is also 7. The left-hand limit I got by plugging numbers less than 2 in, but progressively closer to 2, and the y's got progressively closer to 7. None of them actually equaled 7. The right-hand limit I got by plugging numbers bigger than 2 in, but closer to 2. Never did plug in 2, but the numbers got closer to 7. The left-hand limit was 7. The right-hand limit was 7. I would say the two-sided limit must also be 7. So anytime I calculate a left-hand limit and a right-hand limit, if they're the same, then I can drop the little minus and plus sign and do the two-sided limit. Let's do another one which is going to be awful to enter on my calculator. The absolute value of x plus 3 over x plus 3 plus x, ugh. But I want to use my calculator to get the y, so let me try to get this in here. So y equals clear. This is an older calculator. It doesn't do fractions so nice, but we can do it okay. So first I need the absolute value of x plus 3. I hit my math button, so this math button, and maybe over to NUM, and then enter for ABS. So there's the absolute value. So math, NUM, enter on ABS, and then x plus 3. There's the absolute value of x plus 3 for the numerator, and then divide for my denominator, and then the x plus 3 needs to be in a parentheses, and then plus x. So that's how the function I'm going to have to enter on my calculator, because it doesn't enter fractions very nicely. So there's the function that I'm going to try to find the left-hand limit for at 3 and the right-hand limit for at 3. So I can just graph it now. I don't need to zoom anymore. And look at that jump in the graph. That's interesting, I guess. So let me start plugging numbers in. So second calc value. I'm plugging numbers in that are less than 3 but progressively closer to 3. So at 2.5, I get 3.5. At 2.9, I get 3.9. At 2.99, I get 3.99. And at 2.999, I get 3.999. So that's enough for me to know what the left-hand limit is, I believe. I believe that the left-hand limit is 4. That's taking numbers less than 3, but getting progressively closer to 3 and plugging them in. Now to do the right-hand limit, taking numbers that are bigger than 3, but progressively closer to 3. So I'll plug in 3.5 and get 4.5. I'll plug in 3.1 and get 4.1. I'll plug in 3.01 and get 4.01. If I had to guess, this is going to be 4.001. And it is. So again, for a right-hand limit, I'm taking numbers that are bigger than the target value there, the limit value of x, plugging them in. And this also looks like it's 4. So the left-hand limit was 4. The right-hand limit, hey, I should be doing -3. Interesting. Let me recalibrate this in a second. Well, the left and the right-hand limit were 4, so the two-sided limit is 4. What I should have asked, if I wasn't being a moron, is what happens at negative. I should have done this, which is my bad. I should have done this. Let's do this table. I'm going to find the left-hand limit as x approaches -3 of that same function, and the left-hand limit, the left-hand limit as x approaches -3, and the right-hand limit as x approaches -3 of that function. Sorry. First time I'm teaching out of this material, so it's glitchy, but it's okay. So let me find the limit by plugging numbers less than -3. Less than -3 are like -4, -3.5, -3.01, -3.001. Those are all numbers that are less than 3. They're further left on the number line. And then for bigger than 3, like -2, -2.5, -2.9, -2.99 are numbers that are bigger than -2 because -3. Because on my number line, To the left of negative 3 is less than negative 3, but that's like negative 4, negative 3.5, and so forth. To the right of negative 3, like negative 2, negative 2.5, those are numbers that are bigger. So these numbers to the right of negative 3 are good for the right-hand limit, and then to the left is good for the left-hand limit. So let's plug these in real quickly just to make this more interesting. So let me plug in negative 4, and I get negative 5. Negative 3.5, and I get negative 4.5. Negative 3.01, and I get negative 4.01. And negative 3.001, and I get negative 4.001. So I claim that the left-hand limit is negative 4, because those numbers are definitely getting closer to negative 4. And look on the graph, they're getting closer to the bottom jump in the graph. Because they approach from the south side as opposed to the north side. The right-hand limit is going to be this value up there because they're going to approach from the north of that break. So when I plug in negative 2, I get negative 1. When I plug in negative 2.5, I get negative 1.5. When I plug in negative 2.9, I get negative 1.9. And when I plug in negative 2.99, I get negative 1.99. I think those are getting closer to negative 2. In fact, you can see that point right there that it's almost on is probably the point negative 3, negative 2. So my right-hand limit is negative 2. My left-hand limit is negative 4. The two-sided limit doesn't exist in this case. When the left-hand limit and the right-hand limit aren't the same, then you get a D and E for the two-sided limit. Getting closer till we have enough theory to actually do some work. Let's do a limit at infinity with a table. And in order to get my calculator to do a limit at infinity, my x max needs to accommodate the biggest number. So in order to enter this on my calculator to fill out the table to figure out what the limit is as x goes to infinity, to find a limit at infinity, I need to plug in numbers that are close to infinity. 100,000 isn't particularly close to infinity, but close enough. So let me enter the function 8x plus 6 in a parentheses divided by 2x minus 1 in a parentheses and change my window. My x's have to go all the way up to at least 100,000. Let me go to 200,000. Doesn't really matter what the graph looks like. I mean, it does, but it's not looking so great on my calculator right now. Let me make sure. Oh, I changed my y's and not my x's. That's why. Duh. My x's need to go bigger. And bigger than 100,000, 200,000 felt good. This graph flattens out. It's a limit at infinity. Whatever the y-coordinate of that line is going to be what my limit is. Let me figure this out real quickly. What is this limit? I'm going to plug first 100 in, which isn't particularly close to infinity. So let me get closer to infinity and plug 1,000 in. When I plug 1,000 in, I get 4.005. Let me plug 10,000 in. When I plug 10,000 in, I get 4.3 zeros and a 5. And let me plug 100,000 in. When I plug 100,000 in, I get 4.4 zeros and a 5. I think that the limit as x approaches infinity is probably likely 4, because as I take numbers that are smaller than infinity but get closer to infinity, the y's get closer and closer to 4. Let me do another one. Let me skip that one and go to this one, and we'll do a part 3 where I actually start doing some things graphically, finding limits graphically, and see what we happen. So hopefully we understand what limits are table-wise a little bit, graphically a little bit, and now we'll do them by hand a little bit. So let's enter this function. So y equals clear parentheses negative 3x squared plus 1, close out my parentheses, divide it by parentheses x minus 4. So that's the function entered well enough. I'm trying to find the limit as x goes to infinity, so I need to progressively plug in numbers that are bigger than bigger but closer and closer to infinity. This might blow up if I haven't really planned this out well enough. So let me plug in 100. So second calc value, I'm afraid this is going to yell at me. When I plug 100 in, I get negative 312. Now, I'm not even going to include the decimals, they're not important. Now I'll plug 1,000 in, and I get negative 3,012. And let me plug in 10,000, and I get negative 30,012. Well, hopefully I can tell that the y's aren't stabilizing like they did in the last limits. When the y's don't stabilize, then the limit is either positive infinity if they're getting really large, or negative infinity if they're getting really small. And in this case, the y's aren't stabilizing and they're going more and more negative. I would say this limit is negative infinity. That's a bunch of theory. I'm going to do a little more theory as I do some of the problems in the next video. We probably have 2 videos left, so let's pause this.